everyone. Welcome to the Rational and Irrational Numbers Guide and Notes. Let's get started with some definitions. Natural numbers. Natural numbers can be referred to as the counting numbers or positive whole numbers. Counting numbers because when we count the natural numbers. We start at 1 and go 1, 2, 3, etc. Those are the natural numbers. Whole numbers. Whole numbers are the natural numbers plus 0. So 0, 1, 2, 3, etc. Integers. Integers are the positive and negative whole numbers. So for example, -3, -2, -1, 0, 1, 2, 3, etc. Rational numbers. Rational numbers are numbers that can be written as a fraction. Those include all terminating and repeating decimals. Examples would be 1/2, 8, 0.33 repeating, or 0.25. Irrational numbers are numbers that can never be written as a fraction. They are non-repeating decimals. For example, the number pi, square root 2, or square root 3. We are now going to place the above terms in a Venn diagram. We're going to start with natural numbers here in the middle, and then whole numbers will come next. That means whole numbers include all of the natural numbers. Then we have integers. So integers mean that it includes all of the whole and natural numbers plus the negatives of those. Then it comes rational numbers on the outside. That means it includes all of these integer, whole, and natural numbers plus some more numbers. And then off here on the side, we have the term irrational. Numbers that are irrational are not any of these numbers over here. They're not rational, integers, whole, or natural. That's a completely set of different numbers. And on the outside, I'm just going to jot the word real. That's because all of these numbers right here are real numbers. Every real number can be written as a decimal. Every rational number can be written as a repeating decimal. Repeating decimals may be repeating immediately or after a few digits. For example, this number right here, 2.0568, the 8 is the number that will eventually repeat, and 0.7, where the 7 is repeating immediately, are both considered repeating decimals. Let's look at integers written as decimals. Though writing integers as decimals is not common, we could write the number 7 as 7.0 with the 0 repeating. The zeros repeat infinitely. How could you write 1/2 as a decimal? Well, we could write 1/2 as 0.5. Now write 1/2 as a repeating decimal. So that would be 0.50 with the 0 repeating infinitely. 2/5 as a decimal, if you don't know that, 2/5 is the same as, you can multiply each of those by 2. So 4/10, which is 0.4. And as a repeating decimal would be 0.40 repeating. Like I said, we don't usually write numbers like this, but that is what is actually happening. Many fractions you may have memorized in decimal form. However, if you do not know the decimal form of a fraction, you can divide. For example, 1/6 is 1 divided by 6. If you don't know what 1 divided by 6 is, you can just work it out. 1 divided by 6. So 6 goes into 1 0 times. 6 goes into 10 once. Multiply that through. Minus that, you get 4. Bring down a 0. 6 goes into 46 times, and then it repeats. 40 minus 36 is 40, and you can see that this pattern is going to go on forever. So 0.16 repeated. 7/11 as a decimal is, let's divide it. So 7 divided by 11. 11 goes into 70 times. 11 goes into 70 6 times. So that's 66. Subtract 4. Bring down the 0. 11 goes into 43 times. 11 times 3 is 33. 40 minus 33 is 7. Bring down the 0. I get 6. 66. I'm just going to keep going here. And you can see it's going to repeat here. So 7/11 as a decimal is 0.63. And then the 63 will repeat. 5/18 as a decimal. I'm going to divide that. So 5 divided by 18. So 18 goes into 50 twice. 18 times 2 is 36. Subtract that, I get 14. Bring down the 0. 18 goes into 147 times. 18 times 7 is 126. I subtract, I get 14, bring down the 0, and I am going to see that this pattern is just going to repeat. 5/18 is 0.277 repeated. The 7-digit repeats in this fraction. Okay, and this statement at the bottom is something you might want to mark. Every fraction can be written as a repeating decimal. Practice. We are given fractions and we are to write them as decimals and identify the repeating digits. We're given workspace over here to work if we need to divide any out. 1 3/4. You should know that 3/4 is 0.75. So 1 3/4 as a decimal is 1.75. If you don't know that, you can divide it out. The repeating digit here is going to be the 0. There is a 0 invisible after the 5 that will repeat infinitely. 5/11. So let's divide that out over here in our workspace. So 5 divided by 11. 11 does not go into 5. 11 goes into 54 times. 11 times 4 is 44. So I subtract that, I get 6. Bring down the 0. 11 goes into 66 5 times, which is 55. Then subtract that and I get 5. Bring down the 0. 11 goes into 55 4 times. Keep going here, subtract. And I can notice that this is starting to repeat. So it's going to be 0.4545 repeating. So I'm going to write that 0.45 with the line over the 4 and the 5. The repeating digits are the 4 and the 5. 4/9 as a decimal. Let's divide that out. So 4 divided by 9. 9 does not go into 4, but it does go into 40 4 times. 9 times 4 is 36. Subtract those. Bring it down. The 0 down. 9 goes into 44 times. And I can see that this pattern is just going to keep repeating. So 4/9 is 0.4 with the 4 repeating. Last one, 3/8. So let's go 3 divided by 8. 8 does not go into 3. 8 goes into 33 times. 8 times 3 is 24. Subtract, I get 6. 8 goes into 67 times, which is 56. Subtract 4, bring down the 0. 8 goes into 45 times. And right there, my decimal ends. So my decimal is 0.375, and what repeats? 0. That is my infinitely repeating digit. So every single fraction can be converted into a repeating decimal. And every repeating decimal can also be converted into a fraction. Some decimals, such as 0.3 repeating, you may already know the fractional form as 1/3. However, other repeating decimals such as 0.35 with the 5 repeating, you may not know the fractional form. Let's learn how to convert any repeating decimal into a fraction. All right, so let's say we want to convert 0.355 repeating into a fraction. We let x equal the repeating decimal. So x is going to equal 0.35 repeating. We want to create two equations that we can subtract to cancel out the repeating decimals. We want two different equations that have only the repeating digits to the right of the decimal. We are starting with x equals 0.35 with the 5 repeating. Since 3 is on the right of the decimal, so see the 3 right here, but is not a repeating digit, let's multiply this equation by 10. So you can see that right here. If I have x equal 0.355 with repeating, I'm going to multiply it by 10. So now 10x equals 3.55 repeating. Let me just write that out over here so you can see it a little bit better. If x equals 0.35 with the 5 repeating, 10x is going to move this decimal over one spot. So it's going to be 3.5 with the 5 repeating. This is one equation, but we need another one. So let's multiply by 10 again. We're just going to keep multiplying by 10 until we have two equations that have the repeating digits to the right. So if 10x equals 3.5 with the 5 repeating, I'm going to multiply by 10. So 100x is going to be, I'm going to move this decimal over again. So it's going to be 35.5 with that 5 repeating. Now we have two different equations with only the repeating digits to the right of the decimal. You see that right here? We have 100x and we have 10x. The repeating digits are to the right of the decimal. Now we are going to subtract the equations. That will cancel out the repeating digits. So if I take 100x equals this and minus 10x, so if I subtract these digits, these will cancel. And I will just get 35 minus 3, which is 32. 100x minus 10x is 90x. So 90x equals 32. I'm going to divide each side by 90, and I get x equals 32 divided by 90. And if I were to simplify that, I can divide both of those by 2. I get 16 over 45. Let's convert point 1, 2, 3 repeating, so 1, 2, 3, 1, 2, 3, 1, 2, 3, into fraction form. So x will equal what I am trying to write as a fraction. So x will equal my number. So 1, 2, 3 repeating. Remember, we want to create two different equations so that the repeating digits will cancel when subtracted. X equals 0.123 repeating can be one equation since only the repeating digits are to the right of the decimal. There's no other digits that are not repeating to the right. So x can equal 0.123 repeating. My 10x, meaning I'm multiplying each side by 10, so my decimal is going to move over one spot. 10x will equal 1.231231. This equation won't work because the repeating digits right here, if I were to subtract them, they're not going to cancel out. I need the digits to be exactly the same on the right of the decimal. If I do 100x, so I multiply this by 10, I move the decimal over one spot, I get 12.312, and that's my 100x. Could I use those two equations? And I could not, because these will not cancel out when I subtract because they're not the same. So if I multiply by 10 one more time, move the decimal over one more time, I get this equation. This equation and this equation will work because the repeating decimals to the right will cancel because they are the same. Now we will subtract the two equations for which the decimals will cancel out. So we're going to put our larger value up top. So we have 1000x equals 123.123, and we're going to subtract x equals 0.123. When we subtract those, these decimals right here will cancel out. So we have 1000x minus x, which equals 999x. 123 minus 0 is 123. Then if we divide each side by 999, we get x equals 123 divided by 999. Both of those you can divide by 3, and we get 41 over 333. Okay, let's convert these numbers right here to fractions. It gives me 0.51 with the 1 repeating. So I'm going to have x equal my number that I'm starting with, 0.51 repeating. And then I'm going to start multiplying by 10 until I get two equations that I can subtract. So 10x is, move my decimal over one spot, 5.1 repeating. And I'm going to need to do it again because I can't use this x one because the 5's over there. So multiply by 10 again. I get 100x equals 51.11 repeating. And I can use these two equations right here because my decimals here will cancel out. So subtracting those, writing my bigger one on top, I get 100x equals 51.1 repeating. And then I have 10x equals 5.1 repeating. Subtract those, I get 100x minus 10x equals 90x. 51.1 minus 5.1, well, all these ones will cancel out. 51 minus 5 is 46. I divide each side by 90. I get x equals 46 over 90. And I can divide each of those by 2, and I get 23 over 45. Okay, 1.24 repeating. So x will equal my decimal. Start multiplying by 10 here. 10x equals, my decimal moves over one spot, so it's 12.42. I guess that would be repeating. Could be 42, 42, 42, right? So those are not going to work because they will not cancel when I subtract them because they are not exactly the same. So let's multiply by 10 again. I get 100x equals 124.24 repeating. Now I can use this equation right here and this equation right here because my decimals are exactly the same and they will cancel when I subtract. So let's put the bigger one up top. So 100x equals 124.24 repeating. X equals 1.24 repeating. Subtract those. 100x minus x gives me 99x. And 124.24 minus 1.24, those will all cancel right there. And I get 123. Divide by 99, divide by 99. So 123 divided by 9 is my fraction. And that simplifies dividing by 3 to 41 over 33. Write and convert your own repeating decimal. You can try this on your own. I'm going to do one, but yours can be different. I'm going to try x equals 0.1 repeating. So my x is 0.1. My 10x is going to be 1.1 repeating. I can stop right there with those two equations because my decimals will cancel out when I subtract them. So let's go ahead and subtract them. I have 10x equals 1.1 repeating, x equals 0.1 repeating. Subtract those, 10x minus x is 9x. These cancel and I get 1 minus 0 is 1. Divide each side by 9, I get x equals 1/9. Now we're going to talk about irrational numbers. All rational numbers have repeating decimals. Therefore, all irrational numbers have decimals that continue infinitely with no repetition. Let's approximate irrational numbers using what we know about perfect squares. Perfect squares are the product of an integer multiplied by itself. So complete the table of perfect squares below. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, and 10 squared is 100. This is going to help us estimate irrational numbers. Let's estimate the value of the square root of 27. Using our perfect squares, we know that the square root of 25 is less than the square root of 27, just because 25 is less than 27, and that is less than the square root of 36. So I'm trying to figure out 27 falls between these two numbers right here. It falls between 25 and 36. So that means the square root of 27 is going to fall somewhere between 5 and 6. Let's take this one step further. Notice that 27 is closer to 25 than 36. Therefore, we could predict that the square root of 27 lies between 5 and 5.5. Okay, so we're going to approximate the square root of 27 on the number line here below. So I know it's between 5 and 6, and I also think it's between 5 and 5.5. We're just going to fill in this number line here. So we have 3, 4, 5, 6, 7, and here's just 5.5. I know that this right here is the square root of 25. This right here is the square root of 36. I don't have to label those numbers up there, but it will help. So the square root of 27 is going to be maybe about right there because it's closer to 25 than 36. So if I go down here, maybe that's about 5.2. Again, these are approximations. Now let's estimate the value of the square root of 95. Let's go back up to my perfect squares chart up here. So 95, square root of 95 is going to be, somewhere between these two numbers because 95 is between 81 and 100. So it's going to be somewhere between the square root of 81 and the square root of 100, which means between 9, because the square root of 81 is 9, the square root of 100 is 10. So it's somewhere between 9 and 10. Approximate the square root of 95 on the number line. So I know it's between 9 and 10 somewhere. I'm just going to go 8, 9, 10, 11, 12. This is 9.5. So this is the square root of 81. This is the square root of 100. So the square root of 95 is going to be over here, closer to 100 than it is to 81. And so going down, I'm going to estimate that's about 9.7. Again, you are just approximating where it's at. Now let's estimate the value of the square root of 15. Use the perfect squares to complete the inequality statement. The square root of 9 is less than the square root of 15 is less than the square root of 16. So these numbers right here, 9 and 16 are perfect squares, and 15 is going to fall between those. So it's going to be between 3 because that's the square root of 9 and 4 because that's the square root of 16. So let's write this on the number line. I know it's somewhere between 3 and 4. So we'll just say 2, 3, 4, 5, 6. This is 3.5. This is the square root of 9. This is the square root of 16. So the square root of 15 is just going to be right below the square root of 16. I'm going to estimate about 3.9. Estimate the value of the following irrational numbers and plot on the number line. Justify your reasoning. So I'm going to jot down my perfect squares here on the top so I don't have to keep flipping to the next page. So the square root of 3 is going to fall right here between 1 and 4 because 3 is between 1 and 4. So the square root of 3 is going to fall between the square root of 4 and the square root of 1. So that means it's going to fall between 1 and 2. So on my number line, let's write the 0, 1, 2, 3, 4. 1 is the square root of 1, 2 is the square root of 4, and I need to figure out the square root of 3. So dividing that up, 1, 2, maybe about right here, the square root of 3, and that's going to be about 1.7. So we'll estimate 1.7. Okay, the square root of 46. Let's go up to my perfect squares here. Square root of 46 is going to fall between square root of 36 and the square root of 49. So that means it's going to fall between 6 and 7. So on my number line down here, let's label this 5, 6, 7, 8, 9. 6.5 is there. This is the square root of 36. This is the square root of 49. And I want to know the square root of 46. So the square root of 46 maybe is about right there. Again, I'm estimating. So I'm going to say about 6.8. One more, square root of 83. That's going to fall, right, if we go up here, 83 is going to fall between 81 and 100 square roots. So that's going to fall between 9 and 10. So let's label my number line here below, 8, 9, 10, 11, 12. And this is 9.5. This right here is the square root of 81. This is the square root of 100. I want to figure out the square root of 83, which is going to be close to the square root of 81. If I'm estimating that, I'm going to see it's maybe about right there. So that's going to be about 9.1. Okay, everybody, that's it for today. Thank you.